All right, getting close here to wrapping up our quadratics unit here with complex numbers. You got a tiny little peek when we were doing the quadratic formula when I started talking about imaginary solutions, and you're like, what is he talking about? Like, I always knew these mathematicians just made a bunch of stuff up. So not all quadratics have real number solutions. A solution that I can see on the calculator in the form of an x-intercept. So mathematicians, hopefully at this point you've seen our history of the imaginary complex numbers over on quizzes. But mathematicians created an expanded number system using the imaginary unit I, okay? The square root of -1, even though you can't get it on your calculator, they'll give you an error message, is I. So we can treat it like a number. So here's how this works. We're going to simplify some non-real radicals. If I try to go to my calculator, I'll even prove it here. Square root of -9. Error, non-real answer. Okay, so here's how this is going to work. We are going to do something, especially since this is right around Halloween time. This is like perfect for this lesson. So the square times -1 times the leftover. So here's basically what we're going to do. We're going to pull the negative out. Okay, I like to say we're pulling an eye out. Ugh, I couldn't find my little eyeball. I was going to yank that out and put it right in the screen and gross you all out, but that's okay. So we pull an eye out when we see a negative, and it makes the value that's left underneath positive. Okay, and so now, well, you're like, well, the square root of 9 is just 3. 3i. We're done. Okay, so that's really the only thing you're having to remember is when you see the negative under the radical, pull an eye out. And if you can break the radical down at that point, do it. But if you can't, 6 isn't a perfect square, we leave it. Okay? Because basically what we're doing is we're saying, hey, I'm multiplying the square root of -1 times this. -1 times 6 would be -6. Okay? It's weird. Trust me, I get it. It's weird. Pull an eye out. Now, 8. Now I got to do a little thinking. Because remember, again, we've got our squares here. 4 will go into 8. So I can break this radical down. And whenever we can break radicals down, we need to. And so what do I end up with? The 2 that's perfect and gets out of radical jail hangs out with the I. And the other 2 that's still in radical jail stays. Okay, so really, seriously, the only thing we are even chatting about is pulling an eye out. But it gives us a whole other world of possibilities here on things we can do. So now we can solve quadratics that have non-reals. We can actually get the answer. So when we solve by square rooting, okay, we've got some options here. So by square rooting, we would want to isolate our x squared term. So we're going to minus the 10 over. Okay, we're not quite by itself yet. We need x squared completely alone before we can do our last step. So we'll divide by 3. Now comes the moment of truth. So if we kind of rewind in our brains to square rooting, the opposite of squared is square root. But remember, there were always 2 things we were thinking about. The first one is, it's always plus minus because there's 2 answers. It's a quadratic. And now not only do I think about the 12, I've got to remember to pull the I out. Oh my. Plus minus, pull an I out if there's a negative. And not only that, oh my gosh, wait. You're like, so I got to think about 3 things. Yep. Plus minus. Do I need an I? Break it down, maybe. We'll put a question mark. So what's my final answer going to look like then if I'm doing all this stuff? So we got the plus minus, we got the I. So square root of 4 is 2. 3 doesn't break down, still acting irrationally. Love that joke. So what's that make my answer look like? I's not in radical jail. 2's not in radical jail. They can hang out. 3 still got to hang out inside. 2 answers, 2 imaginary answers. If I would do my discriminant here, I'd have gotten a negative answer, a negative number. I also can do it by completing the square. So get a little DJ Pi working here. That's right. As we're can't seem to factor at that. So, okay, I'll stop now. Some of you are going to turn me off or mute me, and I don't want that happening. Okay, completing the square. X is alone. Got to move the 30 to the other side in this case. Remember to get your blanks in there too as we do this. And then this is where we do our side work. We take our B. Okay, we're going to have B. We're going to square half B. We're going to add it here. We're going to add it there. Sorry, I can't get that. I can't get that beat out of my mind. I just can't do it. Get this into a binomial square by taking the value I see in the parentheses, or just half of this. Either one would work. And now we're in and ready to square root it. Square root it. Squares cancel here. Remember all the things over here. Plus minus when we square root. Take out the I at this point since there's a negative. Here's the good news. 5 doesn't break down anymore, so we'll leave that as it is. It stays in radical jail. And my last job, now here's the trick part, is to bring the 5 over. This 5 that's here, I can't just put it straight with the I. I'm not multiplying it over, taking it out of here like I did here. Okay? The only time we're going to have a number in with I is if it's coming out of the radical. So what's my answer going to look like? I'm just going to rewrite what I see, but it has to go before the plus minus. It's its own piece. I've had people ask, can I write the minus 5 at the end instead of at the beginning? You could, but it's not normally the way it's written, so I'd kind of frown on it slightly, not like a big frown, just like lip straight across frown here, okay? So it just gave us a few more opportunities, a few more ways to deal with solutions. Now, complex number operations, do not worry about these. These are going to be the easiest thing we do in this section. When we add or subtract complex numbers, the real parts combine and the imaginary parts combine. Okay? We're going to treat I like a variable. Okay? That's the easiest way to think about this. If those were x's instead of i's, you'd be like, oh, this is like first week of Algebra 2. This is great. That's all we're going to do. Find your real parts. Jot down the answer. Find your imaginary parts. And remember, this has a coefficient. -1 plus 5 is 4. This has an I. This doesn't. We can't go any further. If I showed you 7 plus 4x, you wouldn't tell me it was 11x. So we just leave it. We're done. And just like any time we're dealing with operations on anything, be careful of signs. Okay, this negative's here. Take the time, take a moment to distribute that negative through. Now go through and combine like terms. 2 minus 3 is -1. 8 minus 12 is -4. And we move on with our life. Okay? So just treat I like a variable, and you'll be good. All right, let's see. Can we throw a twist into this? There's always got to be a twist, right? All right, we're going to start multiplying here. I got to move me again. There we go. Okay, so one new thing to take into account here. We said before that I equals the square root of -1. So I squared equals -1. You're like, well, how is that? Well, think about it for a second. If I were to square both sides over here, there's I squared, and square root cancel and just leave me with the value underneath. So this, if I ever see an I squared, I just replace it with -1. That's really the rule here. So we do this just like we would if these were x's. 2i times 4 is 8i. 2i times 5i is 10i squared, but I squared equals -1. So I replace that. We'll chat about something here. Okay. So you're like, okay, replace it, 8i minus 10, I'm done. Hardy, why did you just rewrite it and flip the order? Typically, when we're writing answers that have imaginary parts, you write the real part first, the imaginary part second. This is going to be another one of those things. If you get yourself into trouble on delta math or something like that, you may have to screenshot and show me. These are equivalent. But again, technically, when it says standard form, okay, it means real first, then imaginary. So we really want to do it like this, where the I part is last. Just something to consider. Okay, number 10. We got to FOIL this out. So first, 3 times 2 is 6. Then we got outer. 3 times 6i is 18i. We have inner. -i times 2 is -2i. And we got last. My little smiley faced guy in there. -i times 6i is -6i squared. Okay. So what do I find out here? Let's rewrite this. 6 plus 18i minus 2i. -6 times -1 is +6. Okay, and again, I'm doing all this extra stuff in here, so when you're looking at it, when you're doing the assignments and things, you say, oh yeah, that's where that came from. Okay, replace that with -1, that's going to be 6. And then it's just combine like terms. 6 plus 6 is 12. 18 minus 2 is 16. And we're going. Okay, real, imaginary. And so whenever we're doing the multiplying, that's just what to keep in mind. So first, outer, inner, last. So I noticed something this time, though. So I multiply this out. 4i and -4i cancel. 16 minus -1, because I squared is -1. Don't lose the minus on there, though. Don't do it. Minus a negative is plus. And I'm there. Okay. Now, 12 usually is a downfall of people. For those of you, when we were doing some of the factoring things before, if you remember there's a middle term here and you can just work through that, that's great. Otherwise, here's my suggestion for a majority of us on this. Okay, if you see the squared, write it out, because you're less likely to just square both parts and then get the wrong answer because you're going to be missing your middle term. So first, outer, inner, last. See, if I'd have just distributed the squared, I wouldn't have had this piece in the middle. I'd have just had 49 plus I squared, and I wouldn't have got the right answer. So we remember that I squared is just -1. So 49 minus 1 is 48. And 7 plus 7 is 14. Okay? Treat them just like variables. Just like variables. So if you need to have the variable rules out when you're doing this, hey, give it a quick flashback. Okay. One last thing to deal with. We've done add, we've done subtract, we've done multiply. Now we got to do division. This gets a little more interesting. So the complex numbers are called complex conjugates. Ooh, big fancy term there. The product of two complex conjugates is always a real number. Okay, here's basically the rule here we got to remember. No I in the denominator. Okay, that's the rule. When you get a final answer, I can't be down below. So, how do we fix it? Okay, we're going to multiply by this complex conjugate. So what does that mean? That means whatever you are trying to get rid of, you just change the sign of the I term in the middle. But here's the deal. I can't just do it to the denominator. I have to do it to the numerator too. You're like, well, why? Because I don't want to change the value of my problem. If you multiply something and you divide it by itself, what's anything divided by itself? It's 1. It's like I'm multiplying this equation by 1. I'm not changing the value at all. So what we're going to do here is we're going to multiply this through. So 16 minus 8i. Again, it's just the denominator. We can have I as the numerator. That's fine. And then down below, I'm going to do some side work over here. Well, actually, we can just do it right here. First, outer, inner, last. And check out what happens. Those i's cancel. Again, this is 4 minus negative 1. 4 minus negative 1 is 5. And the last thing I have to do before I circle my answer is, we talked about this last section, if all 3 of these had a number in common that I could divide out, I'd have to do that. I'd have to reduce. In this case, they don't. No I in the denominator. I'm good. Okay? 14, same thing. Find that complex conjugate. In the denominator, okay, I don't get to choose here. This is the one that's bad that I need to fix. Change the sign of I. Same for top and bottom. I don't come up here and do 1 minus 4i. Whatever you do for one, you have to do for both. And it's all about the denominator. Keep that in mind. U. All right, this time we're going to write this all out because that's just a whole lot to keep track of. So first, outer, inner, last. And in the denominator, we've got first, outer, inner, last. Okay, and then we'll clean things up here a little bit. Really got to take my time on the foiling because, again, one sign switch is going to mess everything up. So I just want to take my time. Here, 12 times negative 1 is negative 12. Down here, negative 9 times negative 1 would be positive 9. And now I can go through and fix things up. 5 minus 12 is negative 7. 3 plus 20 is 23i. No problem with the I in the numerator. 25 plus 9 is 34. And 15i and negative 15i cancel. Happy, happy, happy. Are we? Okay, and again, nothing goes into all 3 of those, so I can't do anything else. One last piece. Man, it's been a brute of a section here. Electrical circuits. All right, all my future electricians, you're going to be making all the money here. So we're going to simplify this. Electrical circuits contain several components: resistors, inductors, and capacitors. And I am not an electrician, and I realize a little bit of what those things are. Overall resistance is known as impedance. Don't let all the wordiness scare you. It's going to simplify. Just stay with me. Overall impedance can be found by adding all of the components together. Each resistor is a real number value. Each inductor is a pure imaginary number, and each capacitor is a pure imaginary number. Okay, this is all we need to know. We're taking the resistor, we're adding the inductor, we're subtracting the capacitor. Okay? So you're like, wait. So all I'm doing is, okay, this is R, this is Li, this is Ci. So yes, what your brain is telling you right now is correct. All you're doing is taking 6, this is called ohms, this little upside down horseshoe, plus 10 ohms minus 5 ohms. And just treat the ohms like you would any variable. 6 plus 10 is 4. 6 plus 10 is 4. Wow. 6 plus 10 is 16. I was going to have to fire myself for a minute. Minus 5 is 11 ohms. That's my answer. Okay? Looks so complicated with all the words. We get down to it, it's not that bad. Let's do it one more time. Okay? Our resistor is 13 ohms plus. Now, our inductor is 4 and 5 ohms. So, okay, so 4 and 5 minus our capacitor. Okay, it's just one more piece. All like terms. 13 plus 4 is 17, plus 5 is 22, minus 7 is 15 ohms. Okay? So, hey, you're rolling along here pretty good. So what goes with this? Well, you kind of know what goes with this. Okay? This is just some straight up, break it down, add, subtract, multiply, divide, take your eye out, all that good stuff. And then the page after it is an assignment that I got later in the week a little bit, but it's in here. Again, solve by taking square roots, like we did before. Solve by completing the square, like we did in one of the examples in this section. Solve with the quadratic formula. So we're getting a little bit of going back in each place. So we really are only going to have one little piece left here towards the end, solving equations algebraically, and we're going to be through this unit. So I look forward to seeing you then. But for now, keep up the good work, and we'll go from there. Already can figure out.